Welcome to Classes with Atish. Let's continue with our course on kinematics. Let's call it Kinematics 2. So far, we have gone over equations of motion in generic cases and equations of motion in constant acceleration cases. In this lesson, we will go over some tricks and some shortcuts so you can solve your problems much quicker. Okay? So, just as a revision, equations of motion will say generic case. So this is true in all cases, and then constant acceleration case. This is only true when acceleration is constant. So first up, velocity is defined as rate of change of displacement. Okay. When you integrate over displacement v dt, so this gives you change in displacement is the area under the velocity time graph. Okay. Next up, acceleration is change in velocity or rate of change of velocity. Similarly, when you integrate, the change in velocity is the area under the velocity time graph. Okay. We can also say acceleration is d square s dt square. So the second derivative of displacement. Okay. Now, special cases, constant acceleration, v, which is final velocity, is initial velocity u plus at. A is constant acceleration. S is ut plus half at square. And the third equation we know is v square is u square plus 2as. Okay. Now let's go over some special cases. Okay, let's say a body starts with velocity u and under a constant acceleration its velocity goes up to v after a distance s and in or after displacement s and in time t. Okay. What is the average velocity during time t? It is u plus v by 2. Okay. But do remember, this is only applicable when the acceleration is constant. Similarly, displacement will be u plus v by 2 times t. This is the displacement. Now consider a body that is moving with velocity u. Okay. It goes to final velocity 0. So there is a negative acceleration that is happening here, and it stops after this displacement s. Okay. Then if a body then starts with initial velocity nu, where n is a constant, and it stops after a while, final velocity is 0, then the displacement after which it stops will be n square s. Okay. You can try to prove this and maybe respond in the comments below. This is something that's good to remember. So if a body with initial velocity u stopped under a negative acceleration, that's final velocity is 0, and in the process had a displacement of s, then a body with initial velocity nu will stop after displacement n square s. Okay. Okay, the next type of problem that you will get is, what is the distance covered by a particle in the nth second. This is also under constant acceleration. Okay. So let's say a body starts with initial velocity u, and let's say the constant acceleration on the body is a. Let's say after time t1 it moved s1, after time t2 seconds it moved s2, after time t3 it moved s3, at time t4 it moved s4, and so on. In the nth second it moved sn. So first second, second second, third second, fourth second, likewise nth second it moved sn. If the question is what is the distance covered in the nth second, then the formula for that is, so in this case, displacement in the nth second, we can say it is Sn, so which is the total displacement after n seconds minus displacement after n minus 1 second. So that will give me the distance covered in the nth second. The formula for this is u plus a by 2, 2n minus 1. So nth. Okay. Again, you can try to prove this using the equations of motion for constant acceleration case, but it's a formula good to remember. Okay. Next up, we will talk about a set of problems which has a pattern. We can name that pattern alpha beta type problems. Let's define that. So if a body starts at rest equals to 0, it accelerates at acceleration alpha for time t1, okay, and then reaches some maximum velocity, and then it decelerates with acceleration beta for time t2 and v is 0. Okay. Now there are some formulae that you can remember for these cases. So obviously the total time will be t1 plus t2. Okay. First formula. V max, the maximum velocity that this body achieves, is alpha t1, or we can also write beta t2. Okay, very simple. Second, effective acceleration over the entire motion, okay, is alpha beta divided by alpha plus beta. Okay. Third equation. So obviously V max is effective acceleration times the total time, which is t1 plus, or we can say alpha beta by alpha plus beta times t1 plus t2. Okay. Number 4. Average velocity over the time period t is V max by 2. And number 5, we can say the total displacement is half effective acceleration into t square. Okay. So 5 equations that you can remember for the alpha beta type problems. Okay. Another example I want to give is, let's draw a velocity time graph. We know that the area under this graph gives us the displacement. Remember this, ds is v dt. If we integrate s1 to s2 is integral t1 to t2 v dt, or s2 minus s1, which is the change in displacement, is definite integral t1 to t2 v dt. We all remember that. So area under the velocity time graph gives you the displacement. Now let's say a body starts with velocity v, goes constant velocity, and then it goes negative velocity for a certain time, and then it again goes constant velocity and stops. Okay. So let this area be A1, this area be A2, and this area be A3. It's important to remember that area A2 is negative. So the displacement in this case from 0 to whatever T1 would be A1 minus A2 plus A3. Okay. All right. However, the distance covered. So distance covered, you do not need to consider the signage. In that case, it will be A1 plus A2 plus A3. Okay. Next, we will talk about motion under gravity. So in cases of motion under gravity, always remember that it's a constant acceleration case. Although we will later learn that the gravitational constant g changes, but for all purposes we can assume it to be constant near the surface of the earth. Any velocity in the upward direction, we will consider it positive. Any velocity in the downward direction, we will consider it negative. Similarly, any displacement in the upward direction, we will consider it positive. Displacement in the downward direction is negative. And acceleration in this case, g is always in the downward direction, we will consider it as negative. Okay. So just remember this signage. Now, when a body is dropped from a height h, always remember whenever it says body is dropped, it means initial velocity is 0. Okay. So let's say this is height h and a body is dropped from here. So initial velocity is 0. When it reaches the ground, so what's the acceleration that is acting on it? Minus g. Okay. What's the displacement? Also it is minus. Okay. Let's say it takes time t for the fall. Then if we have to calculate t, let's take the equation s equals ut plus half at square. Now s is this displacement. Displacement is minus h. Initial velocity is 0, so ut is 0. Plus half, what is acceleration, is again minus g t square. So we can say minus cancels out, t square is equals to 2h by g. Okay. Or we can say time taken for the fall is root 2h by g. Okay. What is the velocity when it hits the ground? We can use the equation v equals u plus at. Initial velocity is 0, acceleration is minus g into t. Now obviously v in the negative direction we are saying it's negative, so that's why it's coming as negative. So this will be minus g, t is root 2h by g, or we can say minus 2gh. Okay, we'll end the lesson at this today. These are some of the formulae that you can memorize and use it to solve problems in the special cases faster.